And the good news for us is that not all of these coronal mass ejections succeed. Some of them will fail. Some of them will fail because you don't know what the CME is going to encounter on the way out. It may encounter another, at some height, the magnetic field, or it may move sideways. When you do the analysis, it turns out that it may begin to erupt, but then during the eruption, what you do is you form a current sheet underneath this erupting structure, okay? And in this current sheet, you have electric current that is in the same direction as the current inside the CME. So they attract each other. So basically the CME is not entirely disconnected. There is a tether that connects it with the sun, and that's the electric current sheet that forms underneath. Let me show you this. This is actually very, but I have to edit because you.
Do they just like run big computer simulations to try to figure this stuff out?
Yes. Yes. Yes.
Have you had evidence of that magnetic field that causes the equilibrium?
Now watch this movie. Okay. Before I run the movie, this is a cross section of your slinky. Okay, and this is the strapping field. So this slinky cross section, so you have a hook force pointing outward, and you have the ampere force from the strapping field pointing downward. You have perfect balance, but the equilibrium is unstable. If you perturb it slightly, then you see that it's a runaway effect. So when I start to run the movie, what I'm showing here is the magnitude of the current density. So we have enhanced current density inside this highly twisted field. When it begins to move upward, you create a region here with very low density, it's basically vacuum. So you suck in field lines from the outside, but they have opposite directions. So when they reach, they reconnect. And when they reconnect, they form two new field lines. One, so you cut, they interact here, you cut, and you form two new field lines. One that goes like this, and another one that becomes part of your slinky. Okay? But in order to have, before you do the reconnection happens, you build electric current in this region where the two opposite polarity fields interact. That's electric current sheet. And the current in this sheet and the current inside the CME, they're of the same sign, so they attract each other. If you don't dissipate the current in this sheet, your CME will never escape, because the more you stretch it, the more it tries to move out, the stronger this current sheet becomes, and the more it tries to pull it back. Understand what I'm saying? So the only way for this CME to escape is to dissipate this electric current sheet. And you dissipate it by allowing these magnetic field lines to reconnect. If they don't reconnect, the CME will not escape. So, and that's the big question. What are the conditions in these electric current sheets? Do we have high enough resistivity to set the reconnection and let the current sheet dissipate or not? If this doesn't happen, then your CME is doomed to fail. Okay?